Hello, my name is Andrey Prokopenko. I'm from Oak Ridge National Lab in the United States, and today we'll be talking about a single tree algorithm to compute Euclidean minimum spanning tree on GPUs. This is a collaboration with my colleagues from Oak Ridge, Piyush and Damien Lebrun-Grandié. So let us start with an introduction about the problem and our motivation for solving it. So what is a minimum spanning tree, in particular Euclidean minimum spanning tree? Given a weighted graph, a minimum spanning tree is its subgraph that connects all vertices together without any cycles and has the minimum possible total edge weight. An example is shown on the right, where you have a subgraph with few vertices, and the minimum spanning tree is shown in the bold edges. So sometimes we are given a set of points in, say, three-dimensional space, and we want to compute the Euclidean minimum spanning tree of that. So what is Euclidean minimum spanning tree? It is a computed MST on a distance graph for that set of points, and the distance graph is a graph where the number of vertices is the same as the number of points in the data set, and all vertices are connected by edges, so it's a complete graph, and the weight of those edges corresponds to the Euclidean distance between the vertices. And this problem appears in many applications. Our particular interest is the data cluster, in particular the recently developed HDB scan star algorithm, but it also appears in wireless network connectivity, computation fluid dynamics, etc. The goal of this work was to be able to solve this problem efficiently for a very large data set. And by very large data set, we mean tens or hundreds of millions of data points. We focus on the low-dimensional data because our major application is the cosmology simulation, where it's in a three-dimensional space. Throughout the years, there have been developed multiple methods to compute MST on a general graph, but they all are variants of the three classical algorithms: Boruvka algorithm, Kruskal algorithm, and the Prim's algorithm, which were developed in the 20th century. And they all operate on the same general idea of constructing MST iteratively. Each algorithm maintains a set of sets of vertices called components, and then progressively merges them together using a subset of the graph edges. We will not be talking about Kruskal's and Prim's algorithm because in our estimate they don't provide sufficient level of parallelism required for GPUs, so we'll focus on the Boruvka's algorithm from now on. The following diagram provides a brief overview of the Boruvka's algorithm. Each vertex is placed in its own component at the initialization of the algorithm, as shown in the first plot. After a few iterations of Boruvka algorithm, few points are being merged together, so the components become larger. In this particular case, there are 5 components. Next, the algorithm tries to find the closest neighbor for each point that belongs to a different component. For example, the closest neighbor to this blue point is the orange point, and so on. After that, the algorithm chooses the shortest out of all the edges belonging to the same component. So out of the 3 blue edges, it chooses the shortest one. In this case, it's going to be this one. And finally, it merges, following those edges, it merges several components together. So in this case, it merged into 2 components, which becomes the initial state of the next Boruvka iteration. The fundamental difference between regular MST algorithm and the Euclidean MST is in the graph structure. MST operates on a sparse graph, for example, Twitter connectivity graph or anything like that, where the number of edges is a very small fraction of the total possible number of edges. While Euclidean MST operates on the data points and on the complete graph where all the edges are present, so the number of edges is the quadratic with respect to the number of points. Because of that requirement, this distance graph can only be stored implicitly for large data sets. And identifying the neighbors for each point becomes very expensive if using the brute force algorithm, because the number of neighbors to be examined is the whole data set. In order to reduce that number, we need a different approach. So far, we've seen two popular algorithms emerge: a well-separated pair decomposition approach and the dual tree approach. However, from our point of view, neither provides sufficient parallelism to be used on GPUs. Instead, we chose an older approach of combining a classical MST algorithm with a single tree algorithm, while we provide few extra optimizations and an efficient single tree GPU-ready algorithm to produce the inefficient algorithm. Let us now describe the algorithm in more details. We'll start with a brief overview of the algorithm, and then we'll discuss two optimizations that are crucial for a good performance of the algorithm. As I mentioned before, Borovka algorithm is iterative, and each iteration consists of two phases. The first phase, which is the most expensive and crucial one to optimize, is finding the shortest outgoing edge for each of the components. The second phase is merging the components together, that we'll not be talking about because it's straightforward. Finding the shortest outgoing edge for a component can be seen as a nearest neighbor problem with a constraint, and that constraint is that the neighbor has to be from a different component, and followed by finding the minimum out of all the shortest outgoing edge for the points in the same component. And we'll talk about two optimizations that are necessary to prune the number of distance calculation. If those optimizations are not done, then on the later Borovka iterations, the cost of the algorithm becomes quadratic and it becomes infeasible. On the right, I show the general flow of the algorithm. The first two phases are construction of the bounding volume hierarchy, which is the search index that we use in this work, and then initializing the labels, essentially initializing components with a single vertex. The next few steps are performed in a loop. Each sequence of 4 steps is a single Borovka iteration. The first two steps correspond. The first step corresponds to the first optimization, the subtree skipping. The second step performs to the second optimization, which is computing the upper bound. And then the third step is the tree traversal that combines those details. I note by parallel for loops the parallel paradigm that is being used in each case. And the algorithm stops when there's only one component left. In order to understand the idea of the subtree skipping, we first need to realize that when we construct a tree out of the data points, each leaf node of the tree corresponds to a data point, and thus, because every data point carries a membership in a component, the leaf nodes can be associated with the component membership. Given that information, we can do a single bottom-up traversal on the tree, propagating those labels to the internal node. If the two children have carried the same label, then the label of the corresponding internal node is said to be the same. However, if the two children, for example, child 6 and child 7 of the internal node 5 carry different labels, the label of the internal node is said to be invalid, and which means that in the corresponding subtree there exist nodes from different components. So if we given, for example, this set of 3 components, green, red, and orange, and we propagate this information, the tree structure labeling becomes as follows. This is important because, for example, if a green thread traverses the tree and it encounters node 3 and it realizes that the label of the node 3 is the same as the label it is searching for, it can completely bypass and skip this subtree because it knows that all the leaf nodes in that subtree belong to the same component and thus should not be investigated. This is not very important on the early Borovka iterations when the component size is very limited. However, once we grow the components, and particularly on the later Barovka iterations, this becomes a crucial optimization to maintain the complexity of algorithm limited. The second optimization that we do is using upper bounds for the shortest outgoing edge for each component to reduce the number of distance calculation. If we are given a pair of points and those points belong to different components, then the distance between those 2 points can be used to produce an upper bound on the shortest outgoing edges for each component. The goal here is to try to identify such pair of points that are geometrically close. The way we do that is by using a space-filling curve, a z-curve in this particular case. And if 2 neighbors in the sorted indices on a space-filling curve belong to different components, then they're first of all likely to be geometrically close, because that's the whole point of the space-filling curve. So we can use that distance as a reasonable truncation upper bound for the shortest outgoing edge. And once we compute the minimum out of all such pairs, that will provide us with a reasonable bound. Given those 2 optimizations, we can now briefly describe our modified nearest neighbor tree traversal. Without going into too many details, we highlighted in red the major differences with the regular nearest neighbor algorithm. Particulars are we initialize the radius with an upper bound of the component. So instead of infinity, which means we have to examine everything, this is usually set pretty conservative. The second difference is that while we traverse the tree, we also check the membership of the internal nodes, and if they belong to the same component, then the whole subtree is skipped. Finally, once every point identified the shortest edge, or that point dropped out of the calculation, we update the component shortest outgoing edge to be the minimum out of all the edges. So let us now demonstrate the effectiveness of our approach through some numerical results. First, we want to talk about the implementation. We implemented the proposed algorithm using ArborX library, which is a C++ library devoted to geometric search. It is based on the Cocos library, which provides the performance portable on-node parallelism. Essentially, Cocos library abstracts the underlying physical hardware, such as multi-core CPUs or different kind of GPUs, from the user. So we program to the Cocos model, and it allows us to run on a variety of the hardware. ArborX itself is just a C++ library that implements several spatial indexes. Particularly, it implements bounding volume hierarchy, which is very efficient on GPUs for the search. And it provides certain flexibility and performance that is required in this work. Both libraries are open source, and they are available on GitHub at the links provided at the bottom. To produce a comprehensive list of the datasets, we assembled together a combination of real datasets and some artificially generated ones. All the datasets are of low dimension 2 or 3. Some of the datasets correspond to road network or trajectory data. 2 of the datasets correspond to the data from a cosmological simulation. 2 of the datasets correspond to the synthetic data generated using Gantt-Tau generator, which is well known in the clustering community. And finally, we had 3 datasets that use randomly distributed points using normal distribution. As we can see, the sizes of all the datasets are large, with the road network being the smallest one at about 400K, and the cosmological dataset being the largest one at about 500 million points. We start by first examining the performance of our implementation to the existing libraries. Specifically, we compare against MLPack, which is a well-known library based on the dual tree approach. It is a serial library, so we only include it in this plot. And we compare against MemoGFK library, which is a well-separated pair decomposition based approach, which is the best known to us parallel implementation of the Euclidean minimum spanning tree. We'll start with comparing the sequential performance of the libraries on all the datasets on an AMD EPYC CPU using a single core. In terms of the performance, we measure the million features per second, and by feature we mean the number of points multiplied by the dimensions. This way it allows us to compare the 3-dimensional and 2-dimensional sets on the same axis. And as we can see, first of all, we noted that MLPAC is slower than both MemoGFK and our implementation in all the datasets. And this is not surprising because the focus of MLPAC is not on the performance, but rather on the broad algorithm development. Comparing the MemoGFK with RBREX shows that they are competitive and have a parity for most datasets, with a single exception of the GeoLife 24 datasets. Just a brief note about this dataset is that it is a GPS dataset, and it has a peculiar property of some part of the data having a very large density, while other parts of the data are very spread out. The challenge of that dataset is for the linear bounding volume hierarchy is that the underlying structure, the way the bounding volume hierarchy is constructed using space filling curves, is not sufficient to fully resolve this dataset. What it ends up resulting in is a poor quality of the underlying tree, which leads to poor performance. If a faster way is found to compute the tree, or if a high resolution of the space filling curves is used, this can be improved. Next, we want to compare the parallel performance of two algorithms. One is MemoGFK, well-separated pair decomposition approach. With our approach on a variety of hardware, we use AMD EPYC 64 CPU, NVIDIA A100 GPU, and AMD MI250X GPU, of which we only use a single GCD, graphics computing die. The results are as follows. We see that the RBREX implementation is faster by a factor of 4 to 24 than MemoGFK on NVIDIA A100. It is also factor 2 to 12 faster on AMD. We also note that GeoLife dataset remains to be an issue for RBREX, as was in the sequential case. However, even with that limitation, the GPU runtimes outperform the MemoGFK approach. We also observed that the multi-threaded implementation are typically within factor 2 of the MemoGFK, which is the best available multi-threaded implementation of the Euclidean minimum spanning tree. And while it is not clear from this plot, this number 270 actually means that we are able to compute the Euclidean minimum spanning tree for the 37 million point problem under a single second on a single GPU, which was our target. We also wanted to examine the performance of the implementation depending on the size of the data set. For that, we chose to run the implementation using a variety of samples from a large data set. The reason why we chose the sample approach rather than scaling is because we wanted to produce the data set with the same data distribution as the original data set, and sampling is the only way to do that. As we can see, both RBREX approach and MemoGFK approach reach saturation at about 1 million samples, after which they stagnate. This stagnation and the fact that it stagnates and not drops down actually produces means asymptotically linear complexity of the algorithm. We don't have a theory to confirm that. However, in all our practical experiments, that was the case. Finally, we wanted to take a brief overview on the scaling of the individual computational phases of the algorithm. On the left, we show the MEMA-GFK breakdown of the phases, and on the right of the R-breaks. Each bar corresponds, the top level of the bar corresponds to the sequential performance, while the lower half of the bar corresponds to the multi-threaded time, and the number corresponds to the scaling factor. As we can see, MEMA-GFK has 4 phases, out of which we focus our attention on the tree construction in green and the WSPD algorithm in the red. As we can see, WSPD algorithm scales well for all the data sets. So on 64 cores, you get a speed up of 52, which is great. However, tree construction doesn't scale nearly as well within the factor 4, 5, and so on, which means that it becomes a bottleneck for the parallel MEMA-GFK algorithm. In RBRX, on the other side, we have 2 phases, which is the tree construction and the EMST algorithm using the nearest neighbor search. And we can see that both phases scale well on a GPU with the factors of almost 400 in certain situations and about 150 for the tree construction. So none of the parts serve as a significant bottleneck, particularly because the tree construction part is a very small fraction of the overall algorithm cost. We note that the rod network scaling is the worst out of all examples, and this is mostly because it is the smallest data set. It has about 400,000 points, and that is not enough to fully saturate the GPU with work. To conclude the presentation, I'll summarize our results. We developed a performance-portable algorithm, and we wrote an implementation using open source for the Euclidean minimum spanning tree problem. Compared to the best available algorithms, particularly multi-threaded algorithm, our GPU implementation is up to 24 times faster, and our multi-threaded implementation is within the factor of 2 of that. We also, while I didn't talk about it during the presentation, the algorithm that we developed can actually handle certain non-Euclidean distance, such as mutual reachability distance used in HDB scan star, which means that it can serve as the basis of the certain clustering algorithms. Thank you for your attention. And finally, our sponsors are Exascale Computing Project and Leadership Facility at Oak Ridge.